Continuing our inference game, we just saw what happens when we have two ints, which are 32-bit variables, so let's go ahead and try two 64-bit variables. Here I have leafless boldface and affected oddballs as our new two local variables. Compile that, and you'll get this code. And it looks like we've got a new assembly instruction to learn about. And also, I changed it to now show us the full absolute addresses that it has at runtime, assuming that address space layout randomization is disabled, as it is in our lab VM. And the reason I'm showing you the longer addresses rather than the shortened, truncated versions that I've been using thus far is because we can see there's some sort of calculation going on, and the disassembler is telling us that this line, whatever's going on, seems to be calculating an address 5s, 660, and this one 5s, 668. So that probably has something to do with this new assembly instruction that we'll cover here in a second. So this is add upper immediate to PC and store to register. And I'm going to pronounce that like oui PC, the French oui PC. All right, so oui PC. This adds this upper 20-bit immediate to the program counter PC. That's just hard-coded. This add upper immediate to PC, that's part of its name. So PC is going to add 20 to PC and store it into register destination. Okay, so I just said that it takes the encoded immediate as if it were the upper 20 bits of a 32-bit value, with the bottom 12 bits being assumed to be 0, and it adds that to the program counter and stores it into RD. Now I want to point out that the PC value here is the value of PC at the time that it's pointing at the WePC instruction to execute. So unlike things like Jaller that we saw before, Jaller store, unlike Jaller that we saw before, it is going to have the PC of the instruction itself, not the PC plus 4 of the next assembly instruction. So therefore, WePC is good for calculating PC relative addresses. So if you want to find some data and you are able to encode its address as wherever this assembly instruction is plus or minus something, then WePC can help you find that data. And indeed, that is exactly what we see going on here. What's happening is it's doing WePC and it's doing 0 plus PC. So whatever this assembly instruction's address is, here it's 5s, 62E, that now is the address that is going to be in A5. So then the next part, this add I, is adding 50 to that. So basically you'll have to run it through a calculator yourself or take my word for it, but 62E plus decimal 50 equals hexadecimal 5660. So the net result of these two assembly instructions is that it calculated the address, all 5s, 660, placed it into the register A5, and now it is going to do a load double word from A5 plus offset 0 and load that into A5. So what could it be loading? Well, when we skim through this assembly, we don't see any references to leafless boldface or affected oddballs. So in your debugger, you could go and just look at what that is, or you could just step past the load and see which value gets loaded into A5. But basically, we've got two of these sequences, WePC of 0 to get the address, add I to offset from the address, and then load dword. So one way or another, those are probably going to be references to this data of these local variables because they're too big and we can't use the load upper immediate, the LUI, or the add I. Those can only get us 32-bit values. So to get these 64-bit values, it looks like we're going to pluck them out of some memory that is stored just past the end of this assembly. We can't actually see it. 660, 668, well, those are just sort of right past the end of this function. So we can't see it here, but you can see it in your debugger. So go ahead. This is what your stack's going to look like, and go take a look in your debugger at what the net result of running this TwoLongLongs is going to be. Go ahead and stop, draw yourself a stack diagram, and see how that differs with TwoLongLongs compared to two ints.